Every login, API call, and TLS handshake in your environment is really asking one question: can I trust this? As systems scale, manual trust and gut instinct stop working. In this course, you'll see how cryptography and PKI turn that question into a consistent, automated answer across your infrastructure. When we talk about PKI, we're really talking about enforcing 5 core security requirements across the enterprise. Confidentiality means only the right people or systems can see the data. Integrity ensures no one can silently alter that data in transit or at rest. Availability keeps critical systems, keys, and services usable when we need them. Authenticity proves that keys, users, and services are who they claim to be. And non-repudiation gives us evidence that actions actually occurred and can be proven. Everything we cover in this course ultimately serves these 5 pillars of enterprise trust. Anytime 2 systems talk over a network, you have to assume the path between them is hostile. An attacker might simply listen, eavesdropping on unencrypted traffic. They might tamper with data, changing values in transit or after they're stored. They can spoof identities, pretending to be a trusted server or client. They can replay old but valid messages to trick systems into repeating actions. And in a man-in-the-middle position, they can intercept, modify, and forward traffic without either side noticing. PKI and TLS are designed as direct, practical responses to these threats. Let's connect those security goals to the real-world failures they protect against and the cryptographic tools we use. Confidentiality is attacked by eavesdropping. Encryption protects the data. Integrity is attacked by tampering. Checksums, hashes, and MACs reveal unauthorized changes. Authenticity is attacked by spoofing. Authentication protocols and secret or private keys prove who's really there. Freshness is attacked by replay. Nonces and timestamps show that messages are new and unique. And trust is attacked by man-in-the-middle. Certificates and TLS provide verifiable identities and secure channels. To understand PKI, HSMs, and TLS, we first need the basic building blocks of modern cryptography. Symmetric encryption uses one shared key and is ideal for fast, bulk encryption. Asymmetric encryption uses a public-private key pair, enabling identity, digital signatures, and secure key exchange. Hash functions condense data into fixed-size fingerprints that change completely when the input changes. MACs and digital signatures prove both integrity and who actually created or approved the data. Symmetric and asymmetric cryptography solve different parts of the problem. Symmetric encryption uses a single shared secret key for both locking and unlocking. It's extremely fast, so it's used for bulk data like TLS session traffic or VPN tunnels. Its main weakness is key distribution. How do you share that secret with everyone who needs it without exposing it? Asymmetric cryptography uses a public-private key pair. It's slower, but it excels at key exchange and identity. We use it to establish trust and agree on secrets, then switch to symmetric keys for the heavy lifting. Integrity in PKI starts with a hash of the data. That digest is like a fingerprint. Even a 1-bit change produces a completely different result. If we combine that hash with a shared secret key, we get a MAC. Anyone with the key can verify integrity and authenticity, but you can't prove which specific party created it. Digital signatures go a step further. A private key signs the digest, and the corresponding public key verifies it, giving us integrity, authenticity, and true non-repudiation. Almost everything in modern cryptography depends on strong randomness. Your encryption keys, nonces, IVs, and even short-lived key pairs are only as strong as the random numbers behind them. If those numbers are predictable, attackers can recover keys or impersonate secure sessions no matter how strong the algorithm appears. That's why we rely on operating system CSPRNGs and real entropy sources to generate values that are truly unpredictable. With just a few systems, you can manage keys manually. Each pair of systems shares one secret or one certificate. But as soon as you have hundreds or thousands of services, the number of trust relationships explodes. Every system would need to securely exchange and track keys with every other system. That's the key distribution problem. PKI solves it by introducing a central, highly trusted authority. Everyone trusts the CA, and the CA issues and revokes certificates, so trust can scale cleanly as your environment grows. Now we can see how the pieces fit together. At the bottom, randomness feeds everything, creating strong keys and nonces. On top of that, we have the raw materials: symmetric ciphers for fast encryption, asymmetric keys for identity and key exchange, and hashes and MACs for integrity. PKE then orchestrates these into certificates that bind identities to public keys, and TLS handshakes that authenticate parties and negotiate session keys. Finally, revocation and status checking keep that trust accurate over time as certificates are renewed, rotated, or revoked. PKE becomes truly powerful when it's wired directly into your infrastructure. For network access, you replace shared passwords with client certificates for VPN and 802.1x Wi-Fi say, so every connection is tied to a cryptographic identity. Between services, mutual TLS lets microservices authenticate each other automatically, not just the user or API caller. For device identity, certificates give each server or IoT node a durable, verifiable identity. And for software integrity, code and document signing chain trust back to your PKI roots, so tampered updates and files are rejected before they can do damage. PKE isn't just a cryptographic tool, it's also a governance engine for your organization. When you centralize certificate issuance and key management, you can demonstrate compliance with frameworks like PCI DSS, HIPAA, and ISO 27001 instead of relying on scattered spreadsheets and manual tracking. You also gain strong auditability. Every certificate and key change is logged and attributable. Policy enforcement becomes real, not aspirational. Key sizes, algorithms, and lifetimes are enforced by design. And when incidents occur, you can revoke compromised keys quickly and confidently across the entire environment. In this module, you saw how real threats drive the need for strong guarantees: confidentiality, integrity, authenticity, and non-repudiation. Cryptographic primitives provide the raw materials, and PKI orchestrates them into scalable, enterprise-wide trust. In the next module, we'll go deeper into symmetric cryptography, looking at algorithms, modes, and how they actually protect data in motion and at rest.